Hello. I grew up in Southern California. I spent my elementary days and my middle school, junior high days in Southern California. During the time that the space shuttle was landing in the big dry desert out there, the first 9 shuttle flights were landing there. So I kind of come by this a bit naturally. My elementary school was close enough that I could hear the sonic booms of the shuttle coming in. So my classmates and I wasn't quite like the Apollo era, where if you talk to your average 10-year-old boy, 10-year-old girl for that matter, you probably get a good number of them that say they want to be astronauts when they grow up. It's not that way anymore. With the end of the shuttle program and the perceived end of human spaceflight, which, by the way, is not true at all, you're seeing less kids that are really interested in space, that are really interested in space exploration. And I'll talk about this elephant in the room in a second. I got involved in a jet propulsion laboratory program called the Solar System Ambassadors. And the reason I got involved with that is, as I've worked with schools, as I've worked with, I have a 10-year-old son and gone in and helped out in his classroom, and I talk to the kids, I'm hearing more of them say that they want to be lawyers, that they want to be in finance or business. And I hardly hear any kids that say they want to be astronauts. That concerns me a bit. I don't even hear them say they want to be engineers. So the Solar System Ambassadors Program, there's a couple hundred of us around the country. There's 4 very active right here in Raleigh. We go out and talk to the public. I personally spend most of my time going in and talking to kids. I go into classrooms and try to get them excited about space and about engineering in general. So what I'm going to share with you today is some of the things that I share with the kids. And I hope that it inspires you as much as it inspires the kids. I mostly work with 3rd grade is about the average grade, so you guys are not fidgeting in your seats enough for me. It's really making me uncomfortable, so I need somebody throwing some paper over there, some spit wads. It just makes me more comfortable. So what I'd like to talk to you today is about the planets, is about what the planets can tell us. And there's 3 really big questions that come up over and over again when we're thinking about the planets. And it's the kind of thing that really transcends time. These are questions that have been asked for millions of years. And most recently, you know, within the last couple hundred years, we've come up with a couple of answers. Most recently, in the last 10 or 20 years, we've come up with a lot more answers. Some of those have been gained through the manned space program, through the Apollo program going to the moon, through the space shuttle and the International Space Station. But a lot of them have been gained through unmanned programs launched on rockets like this. So the 3 big questions are, how did our solar system form? Really, really big question. It's got a lot of baggage associated with it. What will happen next? Pretty important question, especially as we look at some of the things that have been talked about today as far as where our planet is going and what concerns we might have there. And probably the biggest question is, do conditions exist elsewhere off of our Earth for life? And how do you answer these questions? Well, a lot of these questions can be answered by studying the planets. How do you study the planets? So let's start with the biggest planet. Let's start with Jupiter. And this will give you kind of an idea of the scale of Jupiter, how big it is in compared to our Earth. And I want to talk about 2 missions today that will give you some idea of what we're doing to go find these things, answer a couple of those questions. And this first one is a mission called Juno. I was fortunate enough to go down to the Kennedy Space Center and watch this mission launch. This is a pretty big spacecraft. It's powered by solar panels. You can see the 3 panels on it. It's tumbling towards Jupiter. The tumbling motion allows it to stabilize as it's flying through space. Each one of those solar panels is about the size of a school bus. And when it was initially launched and did its first almost complete orbit of Earth, those solar panels were producing thousands of watts of electricity. As it gets closer to Jupiter, Jupiter is so far out that it's down to the size or the wattage of a couple of light bulbs. That's how far out it is. Even those are very efficient solar panels. We've come a long way in the past 10 or 15 years on efficiency of solar panels. It really takes a long time. And that kind of boom that's winding around there, the one that's different from the other panels, is going to be measuring the magnetic fields around Jupiter. We want to understand what is going on with Jupiter. But the question ultimately comes up, why Jupiter? Why are we spending money to go out and study these things? Jupiter is described by scientists as a Rosetta Stone of planets. It's large enough that when it was formed, it has been able to retain that mass. It's been able to retain all that material, whereas all the changes that were going on in the inner part of the solar system where we live, these planets aren't massive enough to really retain that. So when we go to Jupiter and study the gases and the clouds that make up the planet, and ultimately the core, we want to understand what's in the core of the planet, we're really studying the beginning of the solar system. So that's very, very important. And as you look at the center of that spacecraft there, that is described as a tank. It's this very well-hardened box that contains all the components and the science instruments. And it is protected from the huge amount of radiation that is coming off of that planet. And this animation here describes how you have to deal with that amount of radiation. Normally when you put a satellite in orbit, when we've got our DirecTV satellites or our XM or Sirius satellite radio, we're going in a pretty regular orbit, and it's pretty close to circular. It's a little bit elliptical, but pretty close to circular. This is a highly elliptical orbit because we can only take glancing blows by the planet. That radiation is so great that it is literally frying that spacecraft as it flies past. Ultimately, this spacecraft is going to die. When I talk to students, they always ask the question, well, what happens next? What happens to these spacecraft when we're done with them? In the case of the Hubble Space Telescope, we're going to have to splash it down at some point, make sure it lands in a nice, safe place. In the case of these spacecraft, generally they just go into a solar orbit, and millions of years from now we'll probably crash into the sun. This one, we're going to purposely crash into the planet Jupiter. And the reason for that is, well, it's going to be dead. Those electronics on board will have served their lifespan and will have been fried. But there's an interesting moon of Jupiter that might help answer that question of, are we alone, or could we have not been alone in the past? And we want to make sure we don't run into that moon. So we're going to purposely put this into Jupiter and fry it on the way down. And this is kind of fun. This was released the day of launch for the Juno mission. These 3 Lego minifigures are on board the spacecraft. They're made out of aluminum. We've got to save weight. Every pound of payload that you put up on a spacecraft costs a lot of money, so keeping this very, very low. And this is part of NASA's education mission as well. We want to get people connected to the things that are going on there, and specifically to the science. And these 3 figures were picked for some very good reasons. It's obvious why the god Jupiter was picked, and he's got his lightning bolts there. Juno is his sister, and she's got her magnifying glass. She's very good at looking through the mist of clouds, which is why the spacecraft was named after her. But also Galileo got us here. He was the first one to spot those moons of Jupiter and help us understand more about how our planet works, or how the solar system works. So I thought this was kind of cool that they put that on board. So the next one I want to talk about is Mars. Mars is a pretty special place. We've spent a lot of time and effort and money going to Mars. And Mars is a very difficult place to get to, a very difficult spot in the solar system to successfully launch a mission and have it perform its duties. We're running about, as a people, 50-50 on success rates with Mars. Sometimes we miss it completely, don't even make it there. Sometimes the spacecraft will crash into the surface. One place that we've had some good success is with rovers. We've got 3 rovers that are on the surface of the planet right now, another one on the way. I'll show you that in a second. The 2 rovers that have served out their lifespan are the rover Sojourner, which is about the size of a skateboard. And we've got Spirit and Opportunity. Opportunity is still rolling around, doing its job. It was planned for roughly 90 days worth of mission, and has gone many times over that. So the dollar per science there is pretty good. And the other rover is Spirit, that is currently stuck in the sand, and we've pretty much given up on her, but she served her purpose very well. So the next rover that we're sending up there is going to help us understand a little more about what conditions exist on the planet that might contribute to supporting life, either in the future, but probably in the past sometime. What's interesting about Mars is it's described as an ice cube that is covered with dirt. And this picture right here was taken with the polar lander that had a kind of a scoop on it, that very similar to a backhoe, but much smaller. This is one of the first scoops that it took of soil and took a picture of. And you see the white showing through there? That's ice. There's not just a little bit of ice, there's a lot of ice on Mars. And there's three things that you need to support life. One of them is liquid water, well, life as we know it. One of them is liquid water. One of them is some sort of an organic material that can ooze around in that liquid water and build up life. And the other is a power source, an energy source. Well, that's the sun. We know that there's plenty of that on Mars. So this is pretty interesting, and we want to build upon that and understand, could Mars have supported life at some time? So this is the rover Curiosity that was launched a couple of weeks ago from the Kennedy Space Center aboard a rocket just like this one, and I actually got it labeled up with the Mars Science Lab logos on it. This is an Atlas V rocket. This is a 1:43 scale of the rocket. And what's special about this rover is it's huge. It's about the size of a Mini Cooper or a small SUV, and it's got the ability not only to do some of the same things the previous rovers did, but it is truly a science lab. It's called the Mars Science Lab. And it can fire a laser remotely, look at the plume of material that is created by that laser, and analyze the rock, which is pretty cool. What that gives us is the ability to look around at our surroundings up there on Mars and make some good decisions on where to go next. These rovers are traveling at under a mile an hour, so you need to plan these things properly. And what you're seeing now is the material that's being analyzed within the rover by X-rays. It was drawn out of the rock with that drill that you saw. We took extra drill bits this time. We learned that after the last mission. Those things wear out, and there is no Home Depot on Mars. So it's analyzing that, pulling in that data, and sending it back to Earth for analysis. This is leaps and bounds more capable than past rovers and past missions. It's really incredible that we can have that sort of thing on board. And there she is with her laser beam. There was a full-size model of this at the Astronomy Days here in Raleigh a couple of months ago, and we stood around and answered questions about this robot. And the folks invariably asked about this red kind of filter up at the top, and I was very pleased to be able to tell them, yes, that is a laser. That's pretty cool. But something else I want to point out here, and it's pretty visible here on the screen. If you look at the wheel that is up on the rock, he's kind of got his arm up, balancing himself and using his laser, looking at the contents of that rock. Look at the tread pattern in there. When you're developing a tire or a wheel, this is made out of cast titanium, you need to vary the tread pattern, and that's to give you a better chance of getting unstuck, a better chance of getting over a rock. But also you vary the tread pattern because there's cameras on the back of this rover that look backwards and can be used to understand how far the rover has traveled. Well, might as well have some fun with it, and we think of rocket scientists as being pretty humorless people, but they very much are not. If you look at that tread pattern there, it's actually Morse code. And the very top says J, the very middle says P, the very bottom says L, where the rover was designed, so I think that's kind of fun as well. And you can see the robotic arm there that has the drill bits. The drill bits are stored there on the very front in that circular pattern. There we go. So these rockets are huge, and I wanted to share something personal with you. I put a Space Geek next to this picture so you can see how large this rocket is. This was taken down at the Kennedy Space Center a couple of months ago during that Juno launch. And that is the vehicle, that is the booster, the Atlas V booster, this copper-colored part down here that carried the Mars Science Lab aloft. So I was very honored to be able to be that close to it and really take all of that in. Earth does not want us to leave. We talk about all this exploration, and we talk about the future of Earth, and one thing that I've gotten out of this is understanding that Earth really doesn't want us to leave. It is very hard to get things off of this planet. This rocket is huge, 43 times bigger than this. To give you some scope there's the Statue of Liberty. The rocket itself is pretty heavy. It's about the size of, or about the weight of 4 fully grown elephants. But that's just the beginning. It's about 90% fuel by weight when you lift this thing off. So you compare that in elephants, it's a lot of elephants. So that's the fully fueled mass. It's a fully fueled weight. So, and these things are majestic sitting on the launch pad. And they really just jump off the pad when it's time to launch them, because it takes so much energy to get that mass up there. So something I'd like to leave you with, something that you can do yourselves when you get home, and I encourage you to do this with your kids. I do this on the street. I volunteer with my son's elementary science fair, and I drug about 200 people out into the front yard of the elementary school as the International Space Station was heading over, and pointed it out. A lot of people hadn't seen it before, but this is something you can do all the time. You can take your cell phone out right now, take a picture of that QR code, and it's going to take you to the right place. If you're watching online, you can do the same thing. But what this is a neat service that will send you Twitter updates whenever the International Space Station is going to be passing over. And when you go out and look at that, it's a very bright star, is what it looks like. Moves pretty fast, and it's very, very easy to see. It is so bright. So I want you to go out, take a look at it, bring your kids, bring your family, and remember that there are several people up there. It varies from mission to mission, but there's several people up there that are seeing sunrises every day, multiple sunrises. It takes about 90 minutes for them to go around the Earth. Thank you very much for your time.